Okay. Hi. So this is actually a work in progress, and we have a prototype on network mobility, and this is something that we've been discussing with Ray's group, looking into extension for the future internet architecture project. So, so what I will be talking about is network mobility. So it's different from host mobility in the sense that you have group of addresses moving, group of users moving. So first of all, I think this is an important problem because the ability to access internet anywhere, anytime is becoming increasingly important. And a lot of times we are running applications that we don't really want to get disrupted, even though you change your location. And there's an increasing amount of time we spend while commuting. So this means people are spending more time on the move. So we we kind of expect that the network should provide some kind of service that provides this mobility support. And also, a lot of these cars today, for example, have network access, and a lot of us who fly here, and oftentimes you use the internet service on the plane as well. So the question is, how can these kind of services be more ubiquitous and supported, have additional functionality be built into the internet? So here's an example. So let's say a bunch of users on the plane, and they are using internet. And today what we have is we have some kind of support which allows us to access the internet. I think some of you have used the GoGo Inflight service, for instance. And Boeing actually had a service called Connection Service, which got discontinued. So the users talking to a remote server on the internet on the plane, when the plane moves to a different location, actually the plane could be accessing a different ISP in order to connect to the network. So in that case, we have to have some kind of support so that the network connection is not interrupted. So how do we achieve that? So several goals. We want to have reliability. We really want to have low latency in terms of handoff delay, and also want to have seamless sessions support. So there are definitely several challenges associated with that. When networks do move, there's oftentimes a change of attachment point. Sometimes it happens across the different ISPs. Sometimes it's just within a single ISP. So you may change the service provider, and this naturally can cause disruptions of application sessions. So IETF actually has a working group called NEMO, which tries to address this challenge of network mobility. And basically, the idea there is that they are looking at extension of mobile IP. And we all know that mobile IP has difficulties in terms of deployment. Partly is because you rely on a home agent to be available, and also there are security challenges. So building on mobile IP, I believe is very difficult to have this kind of solution to scale to network mobility challenges. And also, there are triangular routing issues with mobile IP type of solution, meaning that you actually, the routes you end up having is rather suboptimal. And for real-time applications, for applications that require a lot of bandwidth, is actually not very going to be sufficient in terms of just using triangular routing to support those kind of applications. So Boeing, actually some of you may have heard of this service. It was I think it was discontinued, but the idea there is actually quite interesting. The idea is using the BGP, the Border Gateway Protocol, the Inter-Domain Routing Protocol, as it is. Just use it to announce a new prefix when it becomes available at a new location. And obviously, there are definitely scaling issues because as you have more prefixes, there will be more announcements. And we all know BGP today already has scaling issues. If you talk to ISPs and analog, they all worry about routing table size. And with IPv6, the routing table size is going to grow significantly, and if you have lots of routing announcements, routing churn happening, and that will cause problems in terms of the load on the router, as well as in terms of the disruption of the application sessions. And also, Boeing Connection only addresses mobility with across ASs. And oftentimes, we also have just moving around within a single AS. So that's actually a common case. So Boeing actually doesn't address that problem. So the more recent solution is the Google Inflight internet service. That's actually a very interesting service. If you look online, try to find out details about it. It's actually using the connecting back to the cell towers, and the cell towers are structured in the ways that it's facing to the sky. So the problem is that this is a very proprietary technology. Although it allows transparent roaming across cell towers, it doesn't allow you to easily add new functionality into the network. And also, you probably are tied with a particular ISP that offers this service. And as we will see, this also can have scaling challenges as well. And we all know that the cellular network today have capacity issues. And a lot of us have iPhones, and it uses AT&T, and a lot of times, and with other ISPs, also has this capacity issues. So instead of depending on just cellular backbone capacity, can we just be more flexible using other type of networks access as well? So this is something that we are proposing in terms of wide area IP network mobility, the WINLAB solution. So first, let me just describe the goals we want to have in terms of inter-AS as well as intra-AS mobility. So we want to have a minimum routing overhead when the network is moved across the attachment points. The attachment points could be associated with different ISPs. And the path inflation in terms of additional length of the path you traverse on the internet should be very minimal. Of course, there's always a trade-off between the overhead of routing announcement and the quality of the path you have. And also, we want to have location privacy because we don't really want people to track except for the network, which has some knowledge of where the prefix is moving. We don't really want to have third party be able to figure out where the network is currently at. And finally, we want to minimize denial of service attack possibilities. So one type of denial of service attack is that someone just try to pretend to be the new location, try to send traffic to a particular destination. So we make several design decisions to address these challenges. First of all, we want to assume a global network infrastructure, meaning that a lot of times the mobile networks just roam within a single AS. We really want to make the common case work well. And occasionally, the network can roam across networks, across prefixes, across ISPs. So we assume there's some kind of infrastructure support. So some ISPs will offer this mobile mobility support. It doesn't require every ISP to offer this service. So it's incrementally deployable. So those ISPs that offer such a mobility support is called mobile ISP. And also, we don't really want to require significant end host modification, meaning that we really don't want the end host clients to have to run new software. And so it has to be incrementally deployable for existing application. And finally, we want to assume that have some kind of infrastructure support to provide security. And that's the only way to ensure that we can prevent denial of service attack. So the solution we adopt is having the mobile ISP set up a AAA server, which is providing authentication, authorization, and accounting. But in any case, they have to provide this service because they want to be able to charge users, for example, for the mobility service. So this is, we believe, a reasonable assumption to have. And finally, we don't really assume the end host have to set up some security authentication amongst themselves. We want to have network to provide this security assurance. So in other words, when you move, you don't want to have arbitrary third party who can listen in your connection and hijack your connection. So that's an important attack we want to prevent. So this is the basic architecture. What's shown here is a mobile ISP which offers the service. As I mentioned before, there is the AAA server, which provides security, authentication, and authorization. And other ISPs do not have to provide the service as long as so AS3 and AS4 can just be participants. So CH stands for the correspondent host, and MH is the mobile host, which uses a mobile IP from a mobile prefix. So it can move from one location to a different location. So let me briefly explain how the Boeing connection service works. So the Boeing connection service is a solution that purely uses BGP as it is. So this means that when the mobile host moves from one location to a different location, so it has previously established a TCP connection, let's say to a server on the internet, and when it moves, then it connects to a new base station, and this causes the network to announce the prefix at a new location. So in this case, actually, it changed to a new ISP. So that ISP has to send a prefix. By the way, connection only supports inter-ISP roaming support, inter-ISP mobility. In other words, if you roam within a single ISP, the ISP has to provide the service. So it's not a complete solution. So as you can see, this can create a large amount of churn if you have lots of prefix moving and moving around from different ISP, across different ISPs. So when you withdraw, and there is a certain amount of time before the routing converges. So in other words, there will be disruption that occurs to your application session. And of course, this increases the number of updates and also increases the BGP table size because the prefix is not easily aggregatable when this prefix is announced by the ISP, the mobile ISP too. And routing instability can occur and temporary loss of routes and performance degradation can also happen from this solution. So what we came up with is a set of techniques which are actually deployable on today's internet with some support from the routers, which can address these limitations from Boeing connection. So first of all, we will assign a set of special prefixes which are mobile prefixes. And this is somewhat a limitation in our solution, but we are looking into scaling this to a larger set of prefixes as well. And also we have designated aggregation routers which help to address the routing scaling issues in terms of not all routers have to keep the state for the mobile prefix. And we use a mobility community for the prefix announcements so that the prefixes can be treated differently compared to other prefixes which are not mobile. And we scope the routing updates so that we don't really have this issue with a large amount of routing churn due to mobile prefixes. And also we have tunnel mapping. So I'll go through some of these details in the later slides. So the end result is that we were able to reduce the number of ASs that need to keep routing state. And that definitely will scale the mobility support much better to a larger number of mobile prefixes. And since we allow aggregation of routing states of multiple mobile networks, this allows us to exchange the routing updates in a more efficient way. And we also reduce the number of routers in the AS that need to keep track of this routing state. So there are some details that I will just briefly mention here. So first of all, we have this assumption that the tier 1 ISPs or some large ISPs will designate a large prefix as the mobile prefix. And subsequently, it can deaggregate these prefixes to its customer. So it can break down into smaller pieces and give those prefixes to the customer. And the sub-prefixes can be announced by any ISPs which provides some mobility support across the internet. And we also have this notion of aggregation router, which essentially are routers in the ISP that advertise these root mobile prefix, which are the top level large prefix, which are designated for mobility service. And only those aggregation router needs to keep track of those routing state associated with the mobile networks. So this is a key design decision we made because it helps us scale the routing updates, because we don't really want all the routers to participate in announcing these routing changes associated with mobile prefixes. And also we have this mobile community which can be just easily added in the BGP updates today, and which indicate that these updates are associated with prefixes which are used for mobility services. Okay, so let me show you an example of what we do for scoping BGP updates. So currently, without scope BGP updates, if you have a mobile prefix which currently is attached to mobile ISP1, when it moves, so previously you have this route announced by mobile ISP1 at some point in time. And so this route is propagated to every other network on the internet. So when this network moves to a different ISP, if you don't do any scoping for the BGP updates, you will have large amount of routing updates announced to everywhere. So in this case, as you can see, the red arrows indicate that these routing announcements will propagate to the entire internet. And all the ASs will need to keep track of the routing state. And this can cause significant routing churn and will be impacting the application sessions. So actually, people have done studies where it shows that it can last up to several minutes in terms of routing convergence. So during those several minutes, certain routers may not have any route to that destination prefix. So that means your application session may get disconnected. So in the scoped way, what we do is when we propagate the prefix attached with the mobility community, so what happens is that this provider AS will have an entry for the mobile prefix in the routing table, and subsequently it decides that it only propagates when it moves around. It decides that it already has this entry in the routing table, so it suppresses the routing updates in the common provider. So because the common provider has the most has this routing information already, so this means that you don't really need to propagate this information to other networks. So there is a disadvantage with this approach. This means that some of the routes will be longer than the shortest routes taken by the policy-based routing. But however, we've shown in the evaluation, the amount of path inflation is very limited because at the top tier ISPs, the routes are already fairly short. Okay, so the other issue is that when you move from one ISP to a different ISP, so how do the traffic, how do the ISPs know where to send traffic? So this is achieved through a tunnel mapping. So in this example, the /16 is the mobile prefix, and sub-prefix of that, which is /24, is used by this plane, which connects to the customer edge 2. So at that point, when it moves to customer edge 2, this new prefix, this sub-prefix needs to be announced to the ISP2 so that the ISP2 knows that traffic needs to be received to that location. So however, ISP1 needs to know that traffic needs to be sent to ISP2 destined to this /24. So how does this do that? So the aggregation router exchanges some information associated with this this prefix, and this is essentially a new entry which indicates, which has this origin information of the tunnel mapping, so that it knows that AR1 knows that this information traffic will be sent to AR2. So this is a fairly simple, small amount of state that needs to be maintained by the aggregation router. So I'll also briefly talk about intra-AS mobility support. This is something actually fairly new because existing solutions do not support that. So what we come up with is essentially very similar to a home agent support, except that the home agent is actually moved into the network. It's one of the routers will be acting as the home agent. So this router is called the designated BGP router. So what it does is it updates this care of address information. And from the host side, we need some amount of support in order to eliminate triangular routing. And this is something, the state information. Okay, so there's a typo. It should be packet mobility state. This is helpful also to prevent denial of service attack and to provide location privacy. So the packet mobility state is essentially a encrypted mapping which associates the home prefix with the current care of address. And it's encrypted using a key which is agreed upon by a set of routers inside the mobile ISP. And you can imagine the routers themselves, we assume, are trustworthy infrastructure, so they can exchange a key periodically amongst themselves. So this is updated when the mobile network switches to a new base station. So what happens is when a mobile network goes to a different base station, we use the AA server to prevent bogus base station from announcing the new location of the mobile prefix. So this binding can be checked by checking the correctness of the token, which is encrypted using the group key agreed upon by a set of routers. And this information is sent back by the correspondent host so that So from the correspondent host perspective, it doesn't really understand what it really means. All it needs to do is, first time it receives this information, it needs to send back so that the routers themselves will figure out how to forward traffic. Because the routers, the correspondent host always talks to the mobile host based on the fixed IP address. The network will figure out where is the most up-to-date current care-of address. So let's see how exactly this works. So the correspondent host uses the home address to communicate with the mobile host. So in this case, the data packet is sent to the mobile ISP, and the data packet is appended with this token information, and this information is forwarded to the correspondent host. All the correspondent host needs to do is echo this information back when it responds with its reply packets, and this information subsequently helps to authenticate whether the correspondent host can talk to the mobile host, and also figures out what is the current care-of address. And once it gets this information, it routes to the current location of the mobile host. So if the mobile host moves to a different location, it will update with the token with the latest care-of address, and this information helps route traffic to the current location. Okay, so with the WINLAB design, we have global mobility, global reachability, and routing optimality. In terms of, we don't really have a lot of path inflation. We have small amount of path inflation, and we have security and privacy guarantee as well as resilience to denial of service attack. And importantly, we also have location privacy, so we don't really expose the location information to end host, to the correspondent host. So I will quickly go through the evaluation results, which is actually all based on simulation. We do have a prototype working, and this is something that as future work we plan to extend to see how we can do evaluation, for example, using the Genie testbed to understand larger scale deployment challenges. So right now we use the simulation just using realistic topologies we gather from route views data. And so the intra-AS topology to evaluate intra-AS mobility, we use the pop-level topologies from the rocket field data. So this is essentially a measurement study collecting the router topology inside various large ISPs. So just a quick summary of the inter-domain mobility support. So here we are basically evaluating the path inflation in terms of how much additional path length you will experience because we are suppressing the WINLAB solution suppresses the routing updates. So this means that you may end up with a slightly longer AS level path than before. So we compare with the connection solution because connection solution is advertising the routes everywhere. So it's the best case in terms of the shortest path used. So as you can see, from the CDF, the amount of increase is only up to 11%. So that's fairly small, and the AS path length did not increase. It increases from 3.951 to 4.403 on average. So it's a fairly small increase. And in terms of the saving, so clearly there's a trade-off, right? So you have slightly longer AS path, but you may you have slightly longer AS paths, but you reduce the amount of routing updates significantly. So this is shown in this figure. As you can see, the red curve indicates the connection solution, which is the Boeing solution, which announces the routing updates everywhere. And the WINLAB solution suppresses the routing updates significantly. So in terms of disruption time, the left figure shows that the amount of disruption time is fairly small. It's only up to about 60 milliseconds based on our simulation. So this is, of course, it can be further reduced by improving the routing design. And this is something that is part of ongoing work. And finally, I want to just briefly show you the intra-AS mobility support in terms of the path inflation delay inflation improvement compared to the NEMO solution. So the NEMO solution, as you recall, is the home agent-based solution, which is essentially mobile IP. So there you have the triangular routing. So this is comparing with our base case of WINLAB. So the amount of inflation you get in terms of path inflation and in terms of delay inflation is fairly large. So this shows that the NEMO solution is actually not a very good idea if you care about real-time applications. So in conclusion, we have proposed this simple idea of how to develop this support IP level mobility, network mobility at a global internet scale. And we have the solution which is fairly low overhead, which has introduces low overhead in terms of producing amount of routing updates and the amount of path inflation. So the cost is slightly higher path inflation, but in exchange we get significantly better scaling at the routing level. So also we have good location privacy as well as protection against denial service attack. So in terms of future work, we're looking at scaling to a larger number of prefixes and also understanding how various mobile applications can make use of this mobility support. This concludes my talk. Any questions? Yeah.
My question is compared to the proxy mobile IP solution, basically this solution changes the hierarchical structure of IP addressing and also some behavior the current BGP does. And the question is how could you achieve this backward compatible and gradual deployment? The goal you also mentioned before?
So in terms of incremental deployment, this is, I think you're right in the sense that there is some challenges associated with the address allocation. So we have this mobile prefix we set aside for mobility service, and we allocate that prefix just for the mobility services purposes. So if you want to have arbitrary prefixes to be used for mobility services, then you have to come up with a solution that is will be able to address this kind of scaling issues. So the mobile proxy solution, I think, has this also limitation in terms of triangular routing, as far as I understand.
Yeah, right now triangle routing has been solved by setting up the tunnel.
Right, so you have to set up tunnels, and also you require some infrastructure support. So this is, we're thinking about the infrastructure support can be moved towards the ISP level, which can be potentially combined with, for example, caching of content. Because the routers will have knowledge that the prefix is moving, so maybe you can also along the way also cache content on behalf of the user. So if you have some, so I think the advantage of pushing this mobility support into the network is that you can make use of this knowledge to offer additional services. For example, caching of content.
Let's say if I'm a service provider, the operator, I have multiple BGPs. I just deploy one or two what we call this aggregate router, right? So then I don't upgrade my other BGPs. Can this solution work?
So if you have more aggregation routers, you will have less path inflation. So you don't really need many aggregation routers. You can just have a single aggregation router in your network, and that aggregation router is responsible for processing the routing updates associated with the mobile prefix. Yeah, so it works for just having a single aggregation router in your network. Yeah, maybe we can discuss more offline. Any other questions? Yeah.
You mentioned how encrypting the care of address protects location privacy with regard to end hosts. Can you clarify a bit more of how many network entities have access to the care of address?
So the care of address information is only is only known to the mobile ISP. The mobile ISP has knowledge of. So the care of address in this case is we're talking about intra-AS mobility. So in that case, you have to. I mean, your mobile ISP will know where you are moving to, right? So I think maybe at the application layer you can provide additional location privacy support. Maybe at the DNS layer, yeah. So in other words, another third party monitoring the routing updates cannot figure out where you have moved to. Okay, thank you.